Okay, the next part of chapter 6 is the binomial probability distribution. So, if we talk about what a binomial experiment is, we are talking about a discrete probability distribution that describes the probabilities for experiments with two disjoint outcomes. Remember, disjoint is that idea that the two events have no overlap, right? Like if one's happening, the other cannot. Think about numbers are either even or odd. There's nothing that's both of those things. So our criteria for today is bins. Think binomial and think, hey, how am I going to remember this? Think bins. That's kind of your acronym to remember stuff. So I would keep that in mind. Good thing to write on a test, etc. on the side to know what's going on. Okay. As we look at the different things, B stands for binary, meaning for each trial, there are two disjoint outcomes. So you've got a success or a failure. I stands for independent, meaning the trials are independent. Remember, independent and disjoint are two different things. It's the idea that the outcome of one trial will not affect the outcome of another. N is number, meaning the experiment is performed a fixed or set number of times. Each repetition of the experiment is called a trial. And then lastly, success. The probability of a success is consistent for each trial. Consistent meaning the same. Okay, so just like we had from 6.1, our random variable is called x. And it's going to be the number of successes that we have. Okay, in this case, it's going to be the number of successes. So, as we think about our similar notations, the number of independent trials will be n. Kind of think about that, like your sample size, the number of trials we've got. The probability of success for each trial is going to be p. Remember we called that like p of x last time? And so therefore, if one's happening or the other, the probability of a failure is 1 minus that probability of having a success. And then finally, x is the number of successes. So that's like your random variable. All right. In these first ones, let's just decide, is this actually a binomial experiment or not? So remember, we're going to do bins. So let's just remind ourselves on this first one before we even read it. Bin stands for what? Binary, meaning there's a success and failure. Independent, meaning each trial doesn't affect the next one. N being the number of trials, a set number. And then S being success, like having a consistent probability rate. Consistent success rate, or success probability. So, a surgical procedure has an 85% chance of success. The doctor performs it on 8 patients. The random variable represents the number of successful surgeries. So binary means, hey, it's either a successful surgery or it is not, right? Independent, just because one person has a successful surgery does not mean the next person will not, or vice versa, right? So yes, each trial is independent. A set number of trials, right? We've got 8 trials, so that looks good. And then a set kind of percent success, which is 85%, so that looks good. All right, so does that meet the conditions? The answer is yes. It does meet the conditions. For these next ones, why don't you take a moment to pause and think about the bins and decide if it meets them or not. All right, as you look at surveying customers entering a sporting equipment store until a customer responds that he or she is shopping for a bicycle, this one does not meet the binomial experiment. I would think about it mostly because of this n, because there's not a set number of trials. As you look at the next one, record the number of songs downloaded in a month for a group of 30 randomly selected college students. I would say here, the thing that stands out to me the most is the B. I would say no, because not binary, right? You're counting the number of songs. That's not even like, hey, you downloaded songs or not. That's not binary. It's not just 2 outcomes. Okay, as we look at our calculator, we will use mostly our calculator today. You can use things like tree diagrams or our formulas. The mean is what we did last time, right? So that can be calculated on our calculator. Same with the standard deviation. well, this is the formula we had. This is what we did with like L1, L2, and we used our 1 var stats, right? Okay, the new thing is we're going to find the probability of getting exactly X successes. So this can also be done on our calculator, but going to be done slightly different than what we did with those two. Okay, what it's showing you down here is how you could do like a tree diagram to figure out that information about, how many people have O negative blood. So as you take a look at this diagram, we're saying, hey, a success is if they have O negative, a failure is if they don't. And as you look at all the outcomes, they're saying, well, how many people from a sample size of 4, so 4 trials, have 0 people with O negative, 1, 2, 3, and 4, and then we get the probabilities over here on the right. You could similarly use the equations here. So if I wanted to find the probability of having 1 person exactly, if I use our 4 choose 1 and multiply by the probability of having 7% that would have a success, and then that 93% is the complement, you would end up with the 0.22522, which matches the table that we had above, or we also see below. Okay. Lastly, if we look at our calculator, and this is going to be the new part, so let's take a look here. We're going to hit, in this case I'm going to clear, we're going to hit second and then vars. If you keep going down the list, we're going to go to binom, in this case PDF, meaning precise, and it asks you for things like trials. So in this case, we had 4 trials. Our probability was 7%, so 0.07, and we're looking, in this case, we were just saying for someone with, let's decide a number. So like, let's try 0%. If we hit paste and then enter, we get 0.4748, and notice that matches the number in our table. You could try that again when we hit second vars. We're going to go down to binom PDF. And I threw the trials and our probability the same, but if I hit 1, notice again this number, if my camera did not want to die, this number matches what we got. So, as a little reminder for you, maybe add this to your notes. We've got binom PDF. We inputted 4, the probability of 0.07, and then 0 for the probability of having 0 people with O negative blood, and we got out 0.748. Okay. Something to notice here is for a fixed p, so for a fixed probability, as the number of trials and in a binomial experiment increases, the probability distribution of the random variable x becomes approximately normal. So, as you look on the left side, these are 3 different probabilities, like a probability of 0.2, of 0.5, and then of 0.8, but they all have sample size n. So if I zero in on this one on the left, our sample size is n equals 15, but if n just equaled 10, I'd have something that looks skewed left. But as I increase it to 30 and then 70, notice how it becomes more and more normal. So with that in mind, we can use the empirical rule as long as the number of trials times the probability of success times the probability of failure is greater than or equal to 10. So remind yourself about the empirical rule. We got 68, 95, 99.7. So the 95 represents that about 95 of the observations lie between 2 standard deviations of the mean. So often we write that as the mu minus 2 of sigma and mu plus 2 of sigma, representing within 2 standard deviations. Within 2 standard deviations of the mean. And then any observation that lies outside that interval may be considered unusual. Okay, I'm going to take a pause there and then come back and I'll